Hi again. So we are moving on to weak bases. So the math associated with finding the pH of weak bases is pretty much exactly the same as it is with weak acids. So first you can see the general equation for how a weak base reacts, right? I just put a general B down there for base. It will react with water. Remember, what it does is it grabs a hydrogen off of the water and leaves behind OH minus. And then this is what you need to solve for to eventually then find pH. So when you're finding the pH of a weak base, often what you do is you find OH minus, then the POH, then 14 minus that. And you can see here's a very common weak base equation. Ammonia is really, NH3 is really the most common example of a weak base. It grabs the hydrogen off of water, it leaves behind OH minus, and there you see the equilibrium constant. A little different this time because it is a basic reaction. We have K sub B, right, for base. There's a few different types of weak bases that we see. One are a group of compounds called amines. Amines are where it has a nitrogen, and the nitrogen, it usually has two hydrogen coming off of it, but it definitely has a lone pair. So at least two, I believe the definition is at least two hydrogen, and with a lone pair. So anytime that you see anything with the word amine in it, so you can see methylamine, hydroxylamine, that's a good chance that it will be a weak base because it's this group and this lone pair that can take the positive hydrogen ion and, opposites attract. So the negative nitrogen or it's electronegative, it has those extra electrons on it. It will attract the positive hydrogen ion from water. Another group of weak acids would be weak bases are the anions of weak acids. So think of after the weak acid donates its hydrogen, what's left? And so that, of course, could be basic, right? F minus, if it's around water, will react and form HF. It will grab a hydrogen off water, right? The acetate, this should really be the weak acid would be acetic acid, right? And the anion would be CH3COO negative. That will react with water and grab a hydrogen off water, leaving behind OH minus. So that could be sodium acetate, potassium acetate, anything acetate, right? If the weak acid is HClO, then ClO negative would be a weak base. H2CO3, that would mean HCO3, and we could even have CO3 2 minus, both of those. Could be anions, that would be basic. This table here is just showing you some common examples, their names and their formulas and their structural formulas and their KBs. These are all going to be also in the back of our textbook in that appendix. So here's this is just a very general question. We have a 0.15 molar solution of ammonia, and the question is asking us to find the OH minus concentration, which we know is just 1 or 2 steps away from finding the pH, right? Writing the balanced chemical equation for whatever you have, for whatever you have acting as a base. So grabbing a hydrogen off of water, that will leave NH4 plus and OH minus. And of course the KB for this is the concentration of the products over reactants. Coefficients become exponents. And we put all those in an ice chart, and we're able to hopefully find the concentration of the OH minus at equilibrium. So here's our NH3. It will react with the water, grab that hydrogen off of water, leaving behind or making NH4 plus and leaving behind OH minus. Our starting concentration of the NH3 was 0.15. We don't worry about the water because it's a liquid. These guys start out as 0. Then this guy will go down by some amount, which the ammonium ion and the hydroxide ion will go up by some amount. These will, of course, become X. And again, with weak acids and weak bases, we are assuming that this right here is negligible. So I'm just going to keep this at 0.15. And then I set up my KB. I can look on that table on the previous page or the back of the book. KB is 1.8 times 10 to the negative 5, and that equals X squared over 0.15. I solve for X, which I have to, this is why it's important to say, what is X? Because in the last set of problems, X was the H plus. Here, X is the OH minus, and it comes out to be 0.00164. I should probably be able to just round that to two significant figures, 0.0016. Of course, if this is the concentration of the OH minus, I can take the negative log of that and find the POH, and 14 minus that to find the pH. Here's another practice problem. What is the pH of a 0.65 molar solution of pyridine? So this is the same type of problem. It is in a multiple choice format, and that's okay. And in this one, like pyridine, that's a lot of numbers. Maybe I'm just going to write base, right? My base plus water reacts with water to make HB plus and OH minus. And I know that the concentration of my base is 0.65. And water doesn't count, and this is 0, 0. And this will be minus X plus X plus X. XX, again, negligible, right? KB is equal to, look it up on the table, 1.7 times 10 to the negative 9. That equals X squared over 0.65. Solve for X. Again, what is X actually the concentration of? It's the concentration of OH minus. And I get 3.32 times 10 to the negative 5. Okay, the question is asking me for pH. So if I take the negative log of the OH minus, right, I'm going to get the POH. And what does that equal? 4.47. And then remember that pH plus POH has to equal 14. So therefore the pH must be 9.52, which is answer choice C. Okay? So really the only difference here between these problems, doing them as an acid or a base problem, is once I get my answer, I will often have to do a little bit more work to find the pH. But honestly, not that much more work. Another practice exercise: which of the following compounds should produce the highest pH? That means, right, most basic, right? The most OH minus concentration. And then it says a 0.05 sample of pyridine, methylamine, or nitrous acid. Well, here what I would be looking for is the KB. The one with the highest KB, remember KB is like any equilibrium constant, the ratio of products over reactants. So if it makes the most products, the products is where the OH minus would be. The more OH minus, the larger the pH. So I would just pick the one with the largest pH. And that actually is methylamine. So I look at those on the chart. Methylamine has a KB of 4.4 times 10 to the negative 4. That's the highest KB of those three that are on there. So that will have the greatest concentration of OH minus and the greatest pH, the highest pH. And this is sort of working backwards. What this is instead of, let me go back to like this question, I gave you the concentration and the KB, find the pH. This is going backwards. This is, here's the pH. You can look up the KB. I want to know the initial concentration. In fact, it actually says the number of moles of the salt, NaClO, that must be added to the 2 liters of water in order to get a solution with a pH of 10.5. Right? So the first thing we need to understand is what's really going on here. Remember, this is a sodium, that's hypochlorite is actually the name of that formula, ClO. Sodium hypochlorite, what is going to react here? The hypochlorite ion will react with water. It will take a hydrogen off of water, and it will leave behind OH minus. The charges should be equal on both sides. If you're like, how come it's, we're adding an H plus to ClO negative, and then those opposite charges will cancel out there. And of course, we know that the Kb would be the concentration of the HClO times the concentration of the OH minus over the concentration of the ClO negative. Now, in order to find the number of moles of NaClO added to the water, I want to solve for that. I want to solve for the denominator in this. And that means I am going to need to have all the other numbers, and I'm going to do, figure that out using an ice chart. So this will be that hypochlorite ion reacting with water, grabbing a hydrogen ion off of water, and leaving behind OH minus. And I don't use X here for like what I don't know. I just don't want it to get confused with this minus X and plus X and plus X. These guys would start out as 0. And then I know that the pH was 10.50. That tells me that the pOH was 14 minus that, or 3.50, which means that the concentration of the OH minus was 10 to the negative 3.50. That comes out to be 3.16 times 10 to the negative 4. So that is this right here, 3.16 times 10 to the negative 4, 3.16 times 10 to the negative 4. I'm going to say that that's still X, or that's still question mark, what I don't know, because when I subtract X, right, for acids and bases, we're saying that that is negligible. So now I can look up the Kb. It is 3.3 times 10 to the negative 7. That's going to be 3.16 times 10 to the negative 4 squared, right, because it's going to be multiplied by itself, divided by that question mark, what I don't know. So what I don't know is the concentration of the ClO negative. I plug that into my calculator, and you can pause the video, do it out, check your work, 0.303 molarity. And now go back and read the question. What does the question ask? It says, how many moles of sodium hypochlorite do I need to add to 2 liters to get this pH? So I need to get the molarity to 0.030. Well, molarity equals moles over liters. My molarity is this 0.030. The mole is what I want to solve for. And remember, it's 2.00 liters. So when I multiply those two, I get 0.606, and that would be moles. And again, just to 2 significant figures, that might be 0.61 moles of ClO negative, which would of course need to come from 0.61 moles of sodium hypochlorite. And the very last question, what is the molarity of an aqueous solution of ammonia that has a pH of 11.17? This is the exact same problem that you just did. So maybe pause it and then try and see if you can figure out the answer. So I'm going to take that NH3, react it with water. What does it make? NH4 plus and OH minus. My initial NH3 concentration, I don't know. These guys start out as 0, minus X plus X plus X. This, right, the X is negligible when compared with the starting concentration. If the pH is 11.17, then the pOH is 2.83, and then the concentration of OH minus, which is what I'm going to need to use, is 0.0014. So that's what these over here are equal to. And then I plug it into my Kb expression, right? Kb is 1.8 times 10 to the negative 5. That's equal to 0.0014 squared, divided by, right, the concentration of the ammonia. Multiply both sides by question mark, divide. Take the square root I get that this question mark that I'm looking at, which is the concentration of NH3 is equal to 0.12 molarity.